Hello everyone. Today I am going to discuss about preparation reactions of alkenes. And this will be the part 1 of the alkenes chapter. I will upload another part. In that I will explain chemical properties of alkenes. And I have already uploaded alkenes chapter. If you haven't seen those videos, let's just check out my channel. In that I have created one playlist with the name of hydrocarbons. In that, we'll get to see all videos related to hydrocarbons. Um, for now, let's get into the day's topic. Let's see the preparation reactions of alkenes one by one. So, let's start with dehydrohalogenation of alkyl halides. So, let's start with dehydrohalogenation of alkyl halides. Alkyl halides, on heating with strong base, undergoes dehydrohalogenation to give alkenes. We will use strong bases such as alcoholic KOH. Generally, alcoholic KOH prefers elimination reaction. So, it is a type of elimination reaction. Let's see one example. So, this. Let's take let's take 1 bromobutane, CH3, CH2, CH2, Br. And in the presence of alcoholic KOH, or we can write it as KOH in ethanol, C2H5OH. Then we will get alkene as a product. Here we will get CH3, CH2, double bond, CH2. We will get propene. There is 1 bromopropane, propane, 1 bromopropane. Here the mechanism is simple. Let me explain you the mechanism also. Here we are taking this 1 bromopropane, CH2, CH2Br. Let's write this hydrogen like this, CH. We are taking this acts like a base and it will obstruct this hydrogen. This bond shift towards carbon and carbon. It will make double bond and this bromine leaves as a living group. Then we will get alternative product. CH3 CH double bond CH2. This is the simple mechanism for this reaction. And one more thing you have to remember is order of reactivity of alkyl halides. Generally, Ri is greater than Rbr, then RCl, and then Rf. Because iodine is good leaving group, better than this chlorine. So it leaves very easily. So in this we have the Sedgwick rule and the Halfman product. Let's see about Sedgwick rule. It states that hydrogen is lost from a beta carbon containing least number of hydrogen in order to produce the most substituted and most stable alkene as a major product. Or in simple words, we can say that. Let's see one example. With that example, you can understand. Let's take this compound CH3, CH2, CHBr, and here CH3 in the presence of alcoholic KOH. Then we will get CH3, CH double bond, CH, CH3. Here we have another probability also, like we will get another product also. This product CH3, CH double bond, CH2. But it is less substituted because see here it is we this product is major product here and this product is minor. So what's happening here is here we have two. See here we have hydrogen CH H and here also we have let's take this hydrogen as H2 and this one is CH2 HD. According to Sedgwick rule, here they mention like hydrogen is lost from beta carbon containing least number of hydrogen. See, according to this statement, least number of hydrogen means here it is beta carbon. This is also beta carbon. And here we have only two hydrogens, but here we have three hydrogens. So we are removing this hydrogen in order to get most stable alkene. So we are getting this most stable alkene as a major product. According to subjective, we will get most stable product. That's it. And opposite to this one is Halfman product. In this, we will get least stable product like and that as major product. Here, if you take this same example, here also, let's take the same example CH3, CH2, CH, Br, and CH2. Generally, we will get Halfman product when we take bulky groups, bulky base. If we take bulky base, then we will get Halfman product like let's see here we will get this product as a major product. Just these two are opposite to each other. This is major product. Less stable alkene, or you can say less substituted alkene. But this is all about this Sejafil and Hartmann product. This thing you should remember here. More substituted alkene undergoes Sejaf. ST means Sejaf product, and less substituted alkene means Hartmann product. This you should remember. And let's move to the next reaction, that is dehydration of alcohols. When alcohols are heated, with a strong acid catalyst such as H2SO4 or H3PO4, they undergo intramolecular hydration, that is elimination of water takes place to form alkenes. This is simply, let's see with one example, then we will get to know very easily. See, here we are taking CH3, CH2, let's take propanol, CH2OH. Then in the presence of concentrated H2SO4 or you can take H3PO4 also acid. You have to take strong acid. So concentrated H2SO4. We have here we will get product as alkene as a product. CH3 CH double bond CH2. Here we are just removing this OH group and we are making bond between these two carbons. Let's see the mechanism. This mechanism also basic mechanism you should know because this is a very simple mechanism. So let's discuss that mechanism. Let's take uh, another example. Here in this reaction, let's take another example and with that example I'll explain the mechanism. CH3, let's take this compound CH, OH, CH3. Here we are taking secondary alcohol. Then, in the presence of concentrated H2SO4, we have this H plus. in this acid. So here we have lone pairs on the oxygen. This lone pairs will abstract this hydrogen, and then we will get CH3, C, CH3, CH3. Here it would be C, OH2 positive. This OH alcohol, this OH will become OH2 positive, and the OH2 positive is a water. It is a good living group. It leaves as a water as a living group. So then we will get after that this water will be removed. Then we will CH3, C, CH3, CH3. Here it will form carbocation. And one more thing you should remember is here there is a possibility of shifting. Like here we have methyl group. So 1,2 methyl shift is possible here because here it is secondary carbocation. But if you shift one of the methyl group to this carbon, then we will get carbon carbocation forms here. So we will get tertiary carbocation. So tertiary carbocation is stability of tertiary carbocation is more than secondary carbocation than primary. So here this 1,2 methyl shift takes place. Methyl shift. Then we will get here this methyl shift. This methyl will be shifted towards this carbon, and here on this carbon we will get positive charge carbocation. So we will get product CH3 C positive CH3 C. Here this methyl group will be here CH3. Then after simply just remove the hydrogen, then we will get alkene as a product CH3 C double bond CH. So CH3 here. For this carbon, we have two methyl groups. For this also, we have two methyl groups. This is the major product and stable. Here, one thing you should remember is in this hydro dehydration, there is a possibility of this carbocation rearrangement. So you should remember this thing here. Just practice this mechanism once, then you will get to know like very easily. In this one, I'll explain you one more example for ring expansion. In this dehydration of alcohols, there is a probability of ring expansion. So let's see with one example for ring expansion case. Let's take this compound. Here it is secondary alcohol. Let's take in the presence of concentrated H2SO4. Same process like this is acid, so we have this H plus. We have lone pairs on this oxygen. This will abstract this acidic hydrogen. Then we will get, then it will form OH2 positive, and we know that water is a good living group, so it will leave as the water. Then carbocation will be formed at that carbon positive. So whenever you have like if you have any ring like this, and then adjacent to that if you have any carbocation, there is a possibility of forming ring expansion. So if you have these type of carbohydrates, then there is a possibility of forming ring expansion. So for our easy understanding, just give just give marking like 1, 2, 3, 1, 2, 3, 4, 5, 6 for our easy understanding and we if you give numbering then you won't do any mistake in this ring expansion. So let's see. Just break this bond here and this this sixth carbon will shift towards the second carbon and one bond will be formed between second carbon and sixth carbon and we will get carbocation on third carbon. Let's see that. Let's give the numbering again. Like here we have one more methyl group. So here 1, 2, 3, 4, 5, 6. Here bond is formed between 2 and 6 and then bond is formed between 2 and 6 and we will get carbocation on the third carbon. So then after here there is a possibility of here there is a possibility of hydride shift because here we have one hydrogen and hydride shift. After hydride shift we will get tertiary carbon. So we will get this one. The final product will be we will get this one as major product and this as minor product. So this is all about dehydration of alcohols. So, and one more thing is in this is dehydration of alcohols of low molecular mass can be affected by passing the vapor of the alcohol over aluminum. Like if you take instead of concentrated H2SO4 or H3PO4, if you take Al2O3 alumina, then also we will get alkene as a product. Let's see one example. Let's take ethanol in the presence of if in questions if they didn't mention any concentrated H2SO4 or if they mention this Al2O3, then there is a possibility of dehydration. Al2O3 at high temperature like 350 to 400 degrees Celsius, we will get CH2 double CH. Let's discuss about third preparation reaction, that is dehalogenation of vicinal dihalides. Here vicinal dihalides means if two halogens will be attached to corresponding carbons like this. These are vicinal dihalides. So here, when vicinal dihalides are heated with zinc in the presence of ethanol or acetic acid, then we will get alkene as a product. So in dehalogenation of vicinal dihalides, we will take zinc in the presence of ethanol as a reagent. Let's see one example. CH3. Let's take this compound CH3. Let's take this compound CH2, CH2. Let's take simple example in the presence of zinc and ethanol and heat. Then we will get ethene as the product. CH2, CH2 plus ZnBr. This is the simple example for this. In this mechanism, no need to remember like just remove this bromine and shift this bond towards here and this bromine leaves as a living group. So just remove this Br2 and make a bond between carbon and carbon. Then we will get alkene as a product. So this is about dehalogenation of vicinal dihalides. Let's discuss another preparation reaction, that is catalytic dehydrogenation of alkynes or controlled hydrogenation of alkynes. Hydrogenation of alkynes in the presence of metal catalyst normally gives alkenes, but controlled reduction of alkanes with H2 gas in the presence of partially deactivated catalysts such as Lindlar's catalyst gives alkenes. So let's see the what is both Lindlar's catalyst. Here in this catalytic hydrogenation, we have two catalysts. One is Lindlar's and another one is Dutch. In Lindlar's catalyst, generally we will use quinoline quinoline as the poison because see here let's take this as surface area and we have small pores on that surface area and if you add this quinoline hydrogen is absorbed on the surface area. If you add this quinoline, uh, this will reduce the surface area and also it will reduce the reactivity rate. It will reduce the reactivity rate. That's why we will get alkene as a product, or else we will get alkene as a product. This is all about quinoline, why we are using quinoline as a poison. So let's see the reagent for Lindlas. Here you should remember this reagent it is more important. That is PDBASO4 in the presence of quinoline. Or you can take CH3COO2. This is the Lindlas catalyst, and you should remember one thing is we will get cis alkene as a product in this Lindlas catalyst. Let's see one example. We will take alkyne product. Let's take this compound CH3, CH2, C triple bond, C, CH3 in the presence of Lindlas catalyst H2 3D BASO4 in the presence of quinoline. Maybe we can use PDCaCO2 also in the presence of quinoline. This is the Lindlas catalyst. We can use anything. Then we will get C H CH3 H CH2H5. See, we are adding these two hydrogens on the same side, which is called cis alkene. In this Lindlas catalyst, when we use this Lindlas catalyst, we will get cis alkenes. We will add these two hydrogens on the same side. So so that's why this is called cis alkene. This let's discuss about Birch reaction. We are calling it as Birch reaction, but exactly it is not a Birch reaction. If you want to know what exactly Birch reaction is, I will upload another video on this topic. So for getting notification, do subscribe to the channel and press the bell icon. Then to you will get the notifications of my videos. So, but you can remember it as words reduction. It's not like in this we will get trans alkene. This was the difference in between that Linda's catalyst and this one. You can remember this as burst reduction itself, but it's not actually a burst reduction. Here, let's see an example. Just remember like this when you take for burst reduction, reagent is sodium in liquid ammonia. This is the important one. You should remember these reagents. Whenever they given this reagent, we will get trans alkenes. Trans alkene is the product. And if they mention this PDDA for 4 and quinoline, then we will get cis alkene. This is the difference between these two things. So let's see one example. Let's take this compound CH3C, double bond C, CH3 in the presence of sodium in liquid ammonia. Then we will get C, double bond C. Here we are adding these hydrogens on the opposite sides. CH3, CH. This is a trans alkene. This is about catalytic hydrogenation of alkenes. So let's discuss about another preparation that is called best method for electrolysis of an aqueous solution of potassium succinate liberates Italian gas at anode. This is the reaction of like it is an electrolysis process and we will get Italian gas. Italian gas is a like Italian is an alkene, so we will get that at anode. Let's see the let's see the example. Here we are taking CH2, CH2 and the COO minus K plus COO minus K plus in the presence of so like we are doing the electrolysis. Then we will get T3 plus we will get CO2 also and KOH plus H. This is about Kolbe's method. And one more last one is cracking of alkenes. Like this is an industrial method. Let's see the examples. And it will occur at a high temperature only. So this is not that important, but we should cover all the topics. So that's why I'm discussing about this one also. This will take place at high temperatures. High temperatures. Like here around 700 degrees Celsius. Then we will get alkene as a product. SH2. If you take propane, then in this there is a probability of cleavage of carbon-carbon bond also. That's why this is not that important reaction. Here we will get one of the products as alkene and ethene also you can get from this. This is all about preparation reactions of alkenes. This is all for today's video. I hope you have understood all the concepts clearly. If you have any doubt, then just let me know through the comment section. I'll go through those comments and I'll try to clear your doubts. And for more videos related to all organic chemistry. Do make sure to subscribe to the channel and share with your friends. And this is all for today's guys. Thank you for watching and let's meet in my next video. Till then, keep practicing organic chemistry. Thank you guys.